All right, Mr. Ellison here, and I am going to walk through a problem with you on calculating projectile motion. Things flying through the air. We do it all the time. Our brains do it with startling accuracy, whether you're throwing a baseball, catching a football, shooting a basket, whatever. Your brain makes these calculations all by itself because you've observed the complete regularity with which the physical world operates. And so your brain doesn't have to figure anything out. Really, it picks up on the pattern over years and years and can calculate the trajectories and forces involved without having to do any math. And yet, we want machines to be able to do things, and so we have to figure out the math so we can predict things. In this case, we're going to figure out how to figure out where something's going to land if we launch it. And in this case, here's our setup for this problem. How far away will a projectile land if it was launched from a 10-meter tower at a 30-degree angle with an initial velocity of 18 meters per second? And there should be a question mark there. All right, so let's start by drawing this. So we're going to draw, here's our little tower, and then there's our ground. We'll make that a tower. So that tower is how tall? It's a 10-meter tower. It's really kind of important to draw things out so that you kind of get a sense of what's going on. And then we're going to make a vector for the initial launch of this object. Okay? And that vector has a value, that's our velocity vector, so it's got a value of 18 meters per second. And if you think about the horizontal line, right there, it's launched at an angle of 30 degrees, right? So that's what the problem gives us. So what do we have to think about? How are we going to determine when this is going to hit the ground? Well, the first thing we have to remember is that we can treat the x direction, the horizontal direction, and the y direction, the vertical direction, completely separately. And the reason is because there is a velocity in the x direction, but there is force being applied by gravity in the y direction. So in the x direction, so it's going to have a component of that velocity that is an angle. A component of that is going to be in the x direction, and that is going to have constant velocity because there are no forces acting on it, right? If something's flying through the air like this way, we do have the force of gravity acting on it, which we'll get to in a moment, but there's nothing pulling or pushing it, assuming we're neglecting air resistance. So x is a constant velocity. And y, we've got this y velocity vector right there, right? And what is y? If there's nothing pushing on anything and something is up in the air, there's one force acting on it, and it's gravity. And we know the acceleration due to gravity, right? So y is going to have an acceleration of, and here's where you have to start to be careful. We're going to call the up direction positive. And so we're going to say the acceleration due to gravity is negative 9.8 meters per second squared. That's meters per second. So that's the acceleration due to gravity. And we're saying for reference, and as long as you keep your frame of reference constant, it really doesn't matter so much what the signs are, what your initial values are, as long as your whole thing makes sense. So now, so the point of this is that it doesn't really matter how fast it's traveling in the x direction. It's the y direction that's going to make the difference, because it's going to go up and then gravity is going to pull it back down. And gravity is pulling straight down, so it's independent of the x direction. Whether or not it just goes boop and lands right there, or it goes boop and lands like there, or it shoots like a bullet. A bullet, neglecting the little bit of lift that a bullet might have, a bullet actually falls to the ground at the same rate. It's just going so fast in the x direction, it hits the ground, however far away it is, depending on the muzzle velocity of the gun, right? So now we have a setup It's pretty clean, looks good. And we're going to have to figure out the time it takes for the ball to go up and then back down and hit the ground. So what we really need first, we need to break, this is at an angle, and we need to break it up into the x vector and the y vector, okay? So how do we do that? That's trig, right? So we're going to start with our so, ka, toa. And let's just solve for both of them right away and get them out of the way. So we basically, what we have is a triangle, right? So we have a triangle with an 18 on the hypotenuse. Then we have our x and our y. And then we have a 30-degree angle, right? So if that's our x, this is a velocity, right? Because that's meters per second. And its initial velocity, so I'm going to put an I, and its initial velocity in the x direction, so I'm going to put an x. And this is the initial velocity in the y direction, so I'm going to put VIY, all right? So let's start with the x one. This is the leg that's touching the angle, so that's going to be cosine, because cosine is adjacent. Adjacent means touching, butted up against. Adjacent, the cosine is the adjacent divided by the hypotenuse. So the cosine of the angle equals the adjacent leg, which in this, I'm going to write it out this way first. The adjacent leg divided by the hypotenuse. Okay? So now we're going to put in the things we know and don't know. The cosine of 30 degrees equals the adjacent leg, that's what we don't know, that's our initial velocity in the x direction, over the hypotenuse, which we know is 18. So now we're going to multiply both sides by 18, and we'll get 18 times the cosine of 30 degrees equals our initial velocity in the x direction. And if you multiply that all out, what are you going to get? You are going to get, where's my notes? 18 cosine 30, you're going to get 15.6. 15.6 meters per second is going to be our initial velocity in the x direction. So now let's do the y direction. And the y is the opposite of this angle, right? So that's going to be the sine. So we're going to be able to say the sine of the angle equals the opposite leg, the ratio of the opposite leg to the hypotenuse. So in our case, we can say the sine of 30 degrees equals the opposite leg, that's our initial velocity in the y direction, over the hypotenuse, which is 18. And again, we'll multiply both sides by 18, and we'll get 18 sine of 30 degrees. And you can kind of see a pattern here. So you don't actually have to write all this out once you're familiar with it. I'm writing it out because it's a teaching video, right? Equals VIY, the initial velocity in the y direction. And this, it turns out, is 9. That's tough, huh? 9 meters per second is the initial velocity in the y direction. All right, so now we have our initial velocity in each direction, and we need to figure out how long it's going to be in the air. And this is the one where you might have to jog your memory a little bit, and that's fine. There's an equation that has to do with time and acceleration and distance, one of the basic equations that we have used. And it goes like this. I'm going to start back over here, I guess. So this equation is the final distance equals the initial distance plus the initial velocity times the time plus 1/2 times the acceleration times the square of the time. I don't know if that looks familiar to you, but if it doesn't, then now it does. All right? So I'm going to replace those x's with y's because that's what we're trying to figure out. And we're trying to find out, we've got the final y distance, the initial y distance plus the initial y velocity times the time plus 1/2 the acceleration in the y direction. There is no acceleration in the x direction, right? Times the square of the time. Now, the one last thing we got to figure out is our y final and y initial, right? And so we got this 10-meter tower up here. And the truth is, it doesn't really matter. You can make the ground 0 and the top of the tower 10. You can make the top of the tower 10. You can make the top of the tower 0, excuse me, which would make the ground -10. And it will come out either way. But it seems natural to make the ground 0, right? So this is going to be 10. So our initial y placement is going to be 10. So that's going to be yi. And this is going to be the final y placement is at 0. But like I say, it just doesn't matter. You could set it the other way, and you'll see in a moment it's going to come out exactly the same. All right, so our y final is 0. And our y initial is 10. And right there, before I go any further, if I had done it the opposite way, I would have had -10 for the final y and 0 for here, which you can see. I'll just subtract 10 from both sides, and it comes out exactly the same, right? All right, plus our initial y velocity, which is 9 times the time, plus 1/2 times the acceleration, which is what? This is where you got to watch the signs. -9.8 meters per second squared times the square of the time. So here we have an equation that's got a constant, a variable with a coefficient, and a squared variable with a coefficient. What does that look like to you? Yes, unfortunately, you have to pull out the mathematician's Swiss Army knife, or one of them anyways, the old quadratic formula. So let's rearrange this so it looks like a quadratic. It's in the right order. So first of all, I'm going to take 1/2 and -9.8 and change that. That's -4.9, right? You guys all okay with that? You all okay with that? Okay, we'll do that. So this is going to be -4.9 t squared plus 9t plus 10. And now we can just stick that in the quadratic formula. And t is the variable we'll stop. Remember, this has to be a 0, by the way. If that's a 0 and you've got this form, you can find out the value of t with the quadratic formula. So we're going to go t equals -b plus or minus the square root of b squared minus 4ac all over 2 times a, right? And we remember that this is a, this is b, and this is c, right? All right. Oh, I got to make sure I remember to keep that on the camera. And move that a little bit. There we go. All right. Can't get lower than the bottom of the paper, right? Okay, so now we're going to stick our numbers in there. So t equals -9 plus or minus the square root of 9 squared minus 4 times -4.9. That's our a term. And then our c value is 10 all over, the whole thing is over it, actually, excuse me, all over 2 times our a value. All right, so once you work that out, you get one positive answer and one negative answer, and you can't have negative time in our world the way we're doing this right now. So you got to choose the positive answer, and it turns out that t equals 2.6. So if we throw something up and the vertical component of the velocity is 9 meters per second, it's going to hit the ground 2.6 seconds later. We just figured that out. Now, we know that for the up and down part, it's going to go up and then back down, and 2.6 seconds later, it's going to hit the ground in the direction in which the acceleration happens, which is toward the center of the Earth, our y direction. Now, all we have to do is use that time and calculate it with our x direction, and we'll know how far it has moved horizontally before it manages to hit the ground. So that's a pretty simple equation. the distance something travels under constant velocity is simply its velocity times the time, right? If you're going, if you are driving 60 miles an hour and you go for 2 hours, you're going to go 120 miles, right? Pretty straightforward. So in our case, we want to know the distance in the x direction. We someday might have to figure out the distance that it travels in the y direction. We could do that, but we're not doing that in the review on the last week of school. The velocity we figured out is 15.6 meters per second. That is the velocity in the x direction, right? And then we just did all this work to figure out the time, 2.6 seconds times 2.6 seconds. So that tells us, that leaves us with our distance is going to be 40.5 meters. And again, if you, hopefully you've been watching this, maybe you've been doing the homework problem that I left you, and you've been doing it along with me, sticking in your own numbers, so you learn this thing. The last thing, you know, I'm just going to tell you what the homework is in case you don't have it anywhere else. The actual assignment is you got to show your work for the assignment. And the assignment is if you have a tower and this tower happens to be 20 meters tall and you're firing the thing off at a 45-degree angle and the initial velocity is 30 meters per second. How far will it go? That's the assignment. So, you remember, you got to show your work, but after you do all the work, it's kind of fun. It feels kind of powerful to go into the PhET lab. And so I'm going to go into the PhET lab, and I got the got our projectile motion PhET lab here. And so I'm going to set up the exact thing we had. It was a 10-meter tower. You can drag this tower up. I should just show you, by the way. You know what? Let me notice there's 4 different labs. There's an intro, there's vectors, there's adding drag, and then there's the lab. You want to click on the lab one. So we're going to take that up to 10 meters. Okay, so there's our 10-meter tower, and it was firing at a 30-degree angle. So I'm going to drag that down to a 30-degree angle. And then here's the initial speed right here, and it's already set at 18. So we calculated that it was going to land 45. Oh, I can't go far enough. So that actually is remediable right up here. You can go minus, minus like that. And then you make yourself a lot more space. And we calculated it was going to land 40.5 feet away. 40.5. All right. And if we did our math right, I'm a little nervous. Not because I don't trust physics, because I don't trust my own math skills sometimes. But here we go. Ready? Bam. Oh, look at that. Right in the bullseye. Excellent. So that's your assignment. Your assignment is what we just said it was right here. Do the same thing with the 20-meter tower. Projectile launched at a 45-degree angle with an initial velocity of 30 meters per second. Work the whole thing out like this. And then try it out on the PhET lab and watch the power that you have with your knowledge of mathematics and physics. See ya.